Sketch the graph of the function f of x equals x to the 4/3 plus 4x to the 1/3 by determining the parts a through I. F of x equals x to the 4/3 plus 4x to the 1/3, two fractional exponents. The denominators of the fractional exponents are the roots. They are each an odd number here, and the domain of an odd root is all real numbers. So for part A, the domain will be all real numbers, or negative infinity to positive infinity. For part B, we want to determine whether there is any symmetry. This is done by evaluating f of negative x and comparing it to the original function f of x. F of x is made up of two fractional exponents. The first has an odd root, the denominator, and an even power, the numerator, so overall it'll have y-axis or even symmetry. The second has an odd root, the denominator, and an odd power, the numerator, so overall it'll have origin or odd symmetry. Since the two terms do not match and they are added together, overall f of x will have no symmetry. F of negative x is negative x to the 4/3 power plus 4 times negative x to the 1/3 power. For the first term, the negative raised to the 4/3, the denominator is the root. The cubed root of a negative is negative. The numerator is the power. Negative to the 4th power is positive. The negative will come out of the 4/3 power as a positive. The x will stay inside of the 4/3 power. For the second term, the negative to the 1/3 power, the denominator is the root. The cubed root of a negative is negative. The numerator is the power. Negative to the first power is negative. The negative will come out of the 1/3 power by being negative and multiplying with the 4 to become negative 4. The x will stay in the 1/3 power. Comparing the first term to the original, it is the same sign. Therefore, f of negative x does not equal negative f of x, and it will not have origin or odd symmetry. Comparing the second term to the original, it is the opposite sign. So f of negative x also does not equal f of x, and it will not have y-axis or even symmetry. For symmetry, it will have none. For part C, we want to determine the y-intercept. This is the point where the graph crosses the y-axis, defined by x equals 0. We can find the corresponding y-coordinate by plugging the x-coordinate back into the original function, y equals f of 0, which will be 0 to the 4/3 plus 4 times 0 to the 1/3. 0 raised to any non-zero positive power will be 0, so this will be 0 plus 4 times 0. 4 times 0 is 0. 0 plus 0 equals 0. If we had an x-coordinate of 0, we found a corresponding y-coordinate of 0, so 0, 0, or the origin, will be the y-intercept. For part D, we want to determine the x-intercepts. These are the points where the graph crosses the x-axis, defined by y equals 0. Y, which is f of x, will be set to be 0, and we want to solve for all x's. It's best to have the function fully factored for this. So back up here, we will factor the function. It has a common factor of a power of x. The lower of the two powers, which is x to the 1/3, can factor out. Factoring it out, we'll leave behind. Factoring is division. Division is subtraction of exponents. We will be subtracting a 1/3 from each. 4/3 minus 1/3 will be 3/3, or 1. So it'll be x to the 1. 1/3 minus 1/3 will be 0, and x to the 0 is a 1 times the 4, which will be a 4. So we have x to the 1, or just x plus 4. y, which is f of x, will be set to be 0, and we can set it equal to the factored version of the function, x to the 1/3 times x plus 4. Since it's factored, we can easily solve for each of the x's. X to the 1/3 equals 0 tells us that x equals 0, because 0 to any non-zero positive power is 0. And the factor x plus 4 tells us that x equals -4. We have a y-coordinate of 0. These are the corresponding x-coordinates. So we have 0, 0, and -4, 0 as the two x-intercepts. For part E, we want to determine the vertical asymptotes. F of x is made up of fractional exponents. Both of them are positive, and there is no denominator. So for vertical asymptotes, there will be none. For part F, we want to determine if there are any holes in the graph. F of x has no denominator, so there will be none. For part G, we want to determine any end behavior, horizontal asymptotes, or slant asymptotes. F of x is made up of two fractional exponents. There is no denominator, so there will be no horizontal asymptotes or slant asymptotes. But because it is powers of x, it will have left end and right end behaviors of positive infinity or negative infinity. We can determine the left end behavior by taking the limit as x approaches negative infinity of f of x, x to the 4/3 plus 4x to the 1/3. Only the highest power term matters here. Negative infinity to the 4/3. The denominator is the root. Cube root of negative is negative. Numerator is the power. Negative to the 4th power is positive. And then infinity to the 4/3 power is infinity. So this equals positive infinity. We can determine the right end behavior by taking the limit as x approaches positive infinity of f of x, x to the 4/3 plus 4x to the 1/3. Once again, only the highest power term matters. Positive infinity to the 4/3 will be positive infinity. And the left end and right end behaviors are the same sign of infinity here, due to the numerator being an even power. For part H, we want to determine the intervals of trend, relative maxima, relative minima, plateaus, and cliffs. All of this involves the first derivative, f prime of x. Taken directly from f of x, the non-factored version. Each term is a power rule. For the first term, bring the power down, 4/3. Subtract 1 from the power, 4/3 minus 1, 4/3 minus 3/3. 4 minus 3, which is a 1/3 power. For the second term, power rule, bring down the 1/3, times it by 4. Multiplying the numerators, 4 times 1 is 4. So it will be a 4/3 x raised to the subtract 1 from the power, 1/3 minus 1, 1/3 minus 3/3, 1 minus 3, which is -2/3. We want to fully factor the first derivative. There is a common factor of a 4/3 as well as an x to the lower of the two powers, which will be the -2/3 power. Factoring out the 4/3, each of these will become a 1. Factoring out the x to the -2/3, factoring is division. Division is subtraction of exponents, subtracting a -2/3, which is equivalent to adding a 2/3. Adding a 2/3 to the first power, 1/3 plus 2/3 will be 3/3. It'll become x to the 1. Adding 2/3 to the -2/3 will be a 0. And x to the 0 equals 1. So we have x to the 1 plus 1. X plus 1 is what's left over. We want all powers to be positive for the first derivative, so we will move the x to the negative 2/3 to the denominator to become a positive power. The 4 will stay in the numerator. The x plus 1 will stay in the numerator. There is a 3 in the denominator, and the x to the negative 2/3 will move to the denominator to become x to the positive 2/3. So we now have the first derivative written as a single fraction. All powers are positive, and it is fully factored. We can now set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. The numerator is factored, and we can see that x will equal a negative 1. From the denominator, x to the 2/3 equals 0 tells us that x equals 0 because 0 raised to any non-zero positive power is 0. We'll now check to see which of these are in the domain. The domain's all real numbers. Each of these are a real number. Each of them are in the domain, and they are therefore both critical numbers. We can now draw a domain line. It has no left end because it starts at negative infinity, and no right end because it ends at positive infinity. We can put all critical numbers on here in order. Negative 1 comes before 0. This splits the domain interval up into 3 separate intervals. We can pick a test value in each of the intervals. The first interval, negative infinity to negative 1, we can pick negative 10. The next interval, negative 1 to 0, there is no integer in there, but we can pick negative 1/2. The next interval, 0 to positive infinity, we can pick positive 10. We can test the trend in each of these intervals by plugging these test values into the first derivative. We only care whether it is positive or negative, so we can plug into the fully factored version. A couple things about this. In the denominator of the fully factored version, we have an x to the 2/3. The denominator is the root. Because it's an odd root, it can be positive or negative. But the numerator, the power, is even. So it'll be squared, and it will always be positive. The 3 in the denominator is also always positive, so that entire denominator is positive. In the numerator, the 4 is positive. All of those positives will not affect whether the overall first derivative is positive or negative. It will solely depend on that x plus 1. So we can plug all of the test values into just the x plus 1. Plugging the negative 10 in, negative 10 plus 1 is a negative. We have a negative first derivative. This corresponds to a decreasing trend. Plugging the negative 1/2 into the portion of the first derivative that matters, negative 1/2 plus 1 is a positive. We have a positive first derivative. This corresponds to an increasing trend. Plugging the 10 into the portion of the first derivative that matters, 10 plus 1 is positive. We have a positive first derivative, and this corresponds to an increasing trend. Right at the critical number of x equals negative 1, we have the trend change from decreasing to increasing. So x equals negative 1 will be a relative minimum. X equals negative 1 did come from the numerator, so it'll be a normal minimum. So we have a relative minimum with an x-coordinate of negative 1. We have a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of negative 1. The best place to plug in for the y-coordinates is the factored version. It's a little easier to work the numbers there. So that will give us negative 1 to the 1/3 power times negative 1 plus 4. Negative 1 to the 1/3 power. 1/3 power is the cubed root to the first power. So cubed root of negative 1, which is negative 1. And then times negative 1 plus 4, which is a 3. Negative 1 times 3 is a negative 3, and we have a corresponding y-coordinate of negative 3. Right at the critical number of x equals 0, we have the trend on the left increasing and the trend on the right also increasing. It's not changing the trend, but x equals 0 is a critical number. It did come from the denominator. If it came from the numerator and the trend didn't change, it would have been a plateau. If it comes from the denominator and the trend doesn't change, it is a cliff. So we have a cliff. It has an x-coordinate of 0. It has a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of 0. Again, plugging into the factored version, 0 to the 1/3 power times 0 plus 4. 0 raised to any non-zero positive power is 0. 0 plus 4 is 4. 0 times 4 is 0. We have a corresponding y-coordinate of 0. For part I, we want to determine the intervals of concavity and any inflection points. All of this requires the second derivative, f double prime of x. Taking this from f prime of x, each term is a power rule. The first term, bring the power down, multiply with the 4/3. 4/3 times 1/3, multiplying the numerators, 4 times 1 is 4. Multiplying the denominators, 3 times 3 is 9. X raised to the, subtract 1 from the power, 1/3 minus 1, 1/3 minus 3/3, 1 minus 3, which is negative 2/3. For the second term, bring down the power, multiply with the 4/3. 4/3 times negative 2/3. Multiplying the numerators, 4 times negative 2 is negative 8. Multiplying the denominators, 3 times 3 is 9. X raised to the, subtract 1 from the power, minus 2/3 minus 1, minus 2/3 minus 3/3, minus 2 minus 3, which is minus 5/3. We want to fully factor the second derivative. There's a common factor in the numerator from the 4 and the 8 of 4. There's a common factor in the denominator of 9. And we can factor out x to the lower of the two powers. That will be the negative 5/3. It's lower by being more negative. So x to the negative 5/3 power. Factoring that out, we'll leave. Factoring out the 4 from the numerator, this will become a 1. This will become a 2. Factoring out a 9 from the denominator, each of these will become a 1. Factoring out the x to the negative 5/3. Factoring is division. Division is subtraction of exponents. We will subtract a negative 5/3, which is equivalent to adding a 5/3. For the first power, if we add a 5/3 to it, negative 2/3 plus 5/3 minus 2 plus 5 is 3/3. 3/3 is a 1. All of that will become a 1. And we have 1x to the 1, or just x. For the second term, adding a 5/3, minus 5/3 plus 5/3 is a 0. X to the 0 is a 1. All of that becomes a 1 times the minus 2. So that'll just be a minus 2. So we have a 1x, or just x, minus 2. There's what's left over after factoring. So it will be an x minus 2. We want all powers to be positive, so we will move the x to the negative 5/3 to the denominator. The 4 stays in the numerator. The x minus 2 stays in the numerator. There's a 9 in the denominator, and the x to the negative 5/3 moves to the denominator to become x to the positive 5/3. So we now have the second derivative written as a single fraction. All powers are positive. It is fully factored. We can now set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. In the numerator, it's factored, so we can see that x equals to positive 2. In the denominator, x to the 5/3 equals 0. X equals 0 because 0 raised to any non-zero positive power is 0. We will now check to see which of these are in the domain. The domain's all real numbers. X equals 2 and x equals 0 are both real numbers. They're both in the domain, and they're both candidate numbers. We can now draw a domain line. It has no left end because it starts at negative infinity, and no right end because it ends at positive infinity. We can put all candidate numbers on here in order. 0 comes before the 2. This splits the domain interval into 3 separate intervals. We can pick a test value in each of the intervals. The first interval, negative infinity to 0, we can pick negative 10. Second interval, 0 to 2, we can pick 1. The third interval, 2 to positive infinity, we can pick positive 10. We can now test the concavity by plugging these test values into the second derivative. We only care whether it is positive or negative, so we'll plug into the fully factored version. That's this one. In the denominator, the x to the 5/3, because it's an odd root, the denominator, and an odd power, the numerator, it can end up being positive or negative. So we have to plug in for each of the x. So plugging in negative 10, in the numerator, negative 10 minus 2 is negative 12, times the 4 will be a negative. In the denominator, a negative 10 to the 5/3, a negative to the 5/3, because they're both odd, will be a negative. Times the 9 will still be negative. We have a negative over a negative, that is a positive. We have a positive second derivative, which corresponds to concave up. Plugging the test value of 1 in, 1 minus 2 is a negative, times the 4 will be negative. In the denominator, 1 to the 5/3 is positive, times 9 will be positive. We have a negative over positive, which is a negative. We have a negative second derivative, which corresponds to concave down. Plugging the 10 in, 10 minus 2 is positive, times the 4 is positive, over 10 to the 5/3 is positive, times 9 is positive. We have a positive over a positive, which gives a positive. We have a positive second derivative, which corresponds to concave up. Right at x equals 0, we have the concavity changing from concave up to concave down. So x equals 0 will be an inflection point. It has an x-coordinate of 0 and a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. We'll plug into the factored version, which is going to be 0 to the 1/3 times 0 plus 4. 0 to the 1/3 power will be 0, and 0 plus 4 is 4. 0 times 4 equals 0. So we have a corresponding y-coordinate of 0. Right at the candidate number of x equals 2, we have the concavity changing from concave down to concave up. And therefore, x equals 2 will also be an inflection point. It has an x-coordinate of 2 and a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of 2, which will be 2 to the 1/3 power times 2 plus 4, using the factored version of f of x. 2 plus 4 is a 6, and 2 to the 1/3 can also be written as cube root of 2. Now 2 is not a perfect cube, so it will have to remain as cube root of 2. But we have 6 times the cube root of 2 as the corresponding y-coordinate. We can now draw the graph. We have a vertical axis and a horizontal axis. The domain's all real numbers, so it'll cover all x values here. There is no symmetry. It does have a y-intercept at the origin. We can label that. It has 2 x-intercepts. One of them is the origin. If the origin is the y-intercept, it will also be one of the x-intercepts because it's technically crossing both axes there. But we have another one also at -4, 0. Label that one. There are no vertical asymptotes, there are no holes. The left end behavior is positive infinity. That means on the left end it's going to end up here. The right end behavior is also positive infinity, so the right end it will also end up here. So we'll be sure that that is the case. Right at -1, -3, there will be a relative minimum. So we'll put a relative minimum there. That's going to be somewhere in here. We'll label that -1, -3. And it'll have a relative minimum kind of shape to it. So something like so. Right at 0, 0, we have a cliff. A cliff is where the tangent goes vertical. So the graph will go vertical briefly there. So right here, it'll take a shape where it'll go vertical, and then it'll change its concavity. It turns out that a cliff is always also an inflection point. And we can see it over here as an inflection point. It actually will be concave up to the left of it and concave down to the right of it. So over here it's going to be concave down. And we also have an inflection point at 2 comma 6 times the cube root of 2. The cube root of 2 is something that's not as low as 1, because the cube root of 1 is 1, but it's not as big as 2. It's somewhere between 1 and 2. 1 point something. And then times 6. So I have a y-coordinate somewhere about equal to 7 to 8, somewhere in that range. And that's where it's going to change from being concave down to becoming concave up again. So that'll be up here somewhere. We can label this as 2 and then 6 times the cube root of 2. And it should be switching over from concave down on the left of it to becoming concave up on the right of it. And now we can connect these pieces together with each other, so we can extend this here and here. And we can be sure that we pass through the intercept here, like so. And we can see that on the left end behavior it is positive infinity, and on the right end behavior it's also positive infinity, as it should be. It is covering the entire domain for the x values of negative infinity to positive infinity, so everything matches up here. And this will be the graph of f of x.